All right, on number one, to write a recursive formula, we need three parts. Remember, we need to give the starting term. In this case, we are told the first term equals 9, so this is the first part of my recursive definition. So I'm just going to start f of 1 equals 9. Now, the second part is my rule, and that rule is based on the previous term. So remember, the way that we write something like this is f of n, that says the current term equals f of n minus 1, and then whatever's happening to get to the next term. So, I mean, we kind of have to examine our sequence here and see what we're doing to get to each term. So I go 9 to 14 to 19 to 24 to 29. We can see that we are adding 5 every time. So my rule would just be to take the previous term plus 5, like that. The last part of my recursive definition is the domain. So if I am starting with the first term, then to use my rule, or I'm sorry, if I'm given the first term, then to use my rule, I won't plug anything in until n equals 2. So my domain for a recursive definition is essentially always just one more than whatever the starting term is. If I started with term 0, then this would be n is greater than or equal to 1. Because in order to use my formula, to get the current term, I need to use the previous term. So to get the second term, I would need to use the first term. So I would start with n is equal to 2. On number 2, we are given a recursive definition, and I want to use that to write an explicit rule. There are several ways that we could go about doing this. It could be useful, or it could be helpful if we make a table and list out some of these terms. So I know the first term is -7. I know then the rule is to multiply the previous term by 3. So I could say the second term is -21. The third term is -63, and so on. That might help you to visualize what's happening here. But for our explicit rule, two parts, right? The first part is the rule, what's happening, what I need to do to get the current term that I'm on. Now, the reason I wrote out the table here is to help us visualize what's happening, right? So I can rewrite this -21 as my starting term of -7 times 3. And then I can write -63 as my starting term times 3 times 3. Right? And then the next one I could write as -7 times 3 times 3 times 3. Or another way of writing that would be -7 times 3 to the second power. This one I could even write as -7 times 3 to the first power. Let me scooch this over a little bit. So times 3 to the first power. This one I could even write as -7 times 3 to the 0 power. So this pattern then, to write my explicit definition, the things that aren't changing here are the -7 and the 3. So whenever we have a geometric sequence, meaning I'm multiplying each time, these two parts are going to remain the same. I'm always going to have my starting term times my growth factor and then raised to a power. Now, in this case, since I started with the first term, this power is always going to be 1 less than whatever term I'm on. So I can write that as the n minus 1 power, okay? Basically what it boils down to is if I am given, or if I have the first term as my starting term, I'm going to use n minus 1 in my explicit formula. If I am starting with term 0 here, then I would just be using n in my explicit formula. Now, we also need to give the domain, and the domain for an explicit definition just tells me where to start. So if I'm starting with the first term, then my domain will be n is greater than or equal to 1. It's just telling me what value to plug in first into my formula. And we can double check our domain if we want by actually plugging this value in for n and making sure that I get out -7. Right? For the next 4, we are determining if the sequence is arithmetic, geometric, or neither, and if it is one of those two, giving the growth factor for a geometric or the common difference for an arithmetic. So to examine these sequences, we're just looking to see if we are multiplying by the same thing every time, adding by the same thing every time, or neither of those. So on number 3, I can see that I am multiplying by 1/2 each time. Now, one way to test this is to take a term and divide by the previous term, and then take a term and divide by the previous term. If we get the same thing every time, when I put that in the calculator, then this would be a geometric sequence. So if I did 31 divided by 62 and 62 divided by 124, and I got the same thing, which I would, right? I would get 0.5 or 1/2, that tells me it's geometric, right? So this is geometric, and my common difference is 1/2 or 0.5. On number 4, I can see that I am adding 3 each time. 8 plus 3 is 11, 11 plus 3 is 14. If I'm adding the same thing each time, this is an arithmetic sequence, and then my common difference is whatever I'm adding. So that would be plus 3 each time. Now, again, one way to test this in the calculator would be to take a term and subtract the previous term. Then take a term and subtract the previous term and see if we get the same thing each time. In this case, we would get 3. On number 5, well, to go from 6 to -2, if I want to think about adding, I would be adding -8. If I want to think about multiplying, I would be multiplying by -1/3. Now, for it to be either arithmetic or geometric, I would have to be doing the same thing to get to the next number. So am I adding -8 to go from -2 to 6? Well, no. I would be adding +8. So it's not arithmetic if I'm adding -8, then +8. We would have to be adding the exact same thing every time. And geometric, well, it's not geometric either, because I'm not multiplying by the same thing every time. If I'm multiplying by -1/3, then I should be multiplying by -1/3 again, but I wouldn't be. I would be multiplying by -3. And again, we can test that going the other way in the calculator. We can just take a term and divide by the previous term, and then take a term and divide by the previous term and see if we get the same thing each time. In this case, this one is neither arithmetic nor geometric. For number 6, this one is kind of tricky because we're going positive, negative, positive, negative. I can tell that I'm not adding the same thing each time, right? To go from 3 to -6, that would be, adding -9. And then from -6 to 12, I would be adding +18. So definitely not arithmetic. Geometric, though, if I think about going backwards and taking a term and dividing it by the previous term, well, -24 divided by 12 would be -2. 12 divided by -6 is -2. -6 divided by 3 is -2. So this one is actually geometric, and my growth factor in this case would be -2. On number 7, just identify the growth factor. So that implies that this is geometric, right? If they're telling us that there's a growth factor. So to figure that out, I know I need to figure out what I'm multiplying by each time. Well, the easiest way to do that is, again, take a term and divide by the previous term. So 81 divided by 27, and then I can also do 27 divided by 9. Both of those would get me a result of 3. Right? So that means I'm multiplying by 3 each time. On number 8, again, same thing. Identify whether this is arithmetic, geometric, or neither. So it helps if we put numbers to this. So in this first figure, I see 4 dots, then I see 7 dots, then 10, and then 13. So if we have numerical values, it's a little bit easier to see the pattern, right? And I can then see that I am adding 3 each time. So if I'm adding the same thing each time, this is an arithmetic sequence, and my, in this case, rate of change or common difference would be 3. Same idea, just from a graph, right? We have to figure out if this is arithmetic or geometric, and then write the recursive definition. So, and again, it might help if we, turn this into a table, list out some terms, so I can see that my first term is 10, my second term is 15, my third term is 20, and so on. Okay, so hopefully we can recognize that the pattern is add 5 each time. So again, 3 parts for my recursive definition. The first part is give the starting term. So in this case, I would say f of 1 equals 10. My starting term is term 1, not term 0 in this case. Then the rule, so I would say to get the current term, take the previous term, and this is that notation. Current term would be f of n, previous term would be f of n minus 1, and my rule that we just came up with is I'm adding 5 every time. And then my domain, since I am given term 1, my domain then will pick up with term 2. That's the first value that I can plug in for n to use this formula that I just came up with. On number 10, we want to write an explicit rule for this table. So let's first try to figure out the pattern, right? 180 to 90 to 45. So I mean, I can tell that I'm not adding the same thing each time, but to check to see if it's geometric, well, we can divide a term by the previous term. So if I do 90 divided by 180, and then 45 divided by 90, 22.5 divided by 45, each time I can see that I would be multiplying by 1/2, right? 180 times 1/2 is 90. 90 times 1/2 is 45. So that means this is geometric, and my growth factor is 1/2. Now, I can, to kind of see the pattern, to see how we can write this formula, we can rewrite 90 as 180 times 1/2. I can rewrite 45 as 180 times 1/2 times 1/2. I can rewrite 22.5 as 180 times 1/2 times 1/2 times 1/2. And then the pattern, right, we can see that if I'm repeatedly multiplying, I can use an exponent. So 1/2 times 1/2 times 1/2 would be the same as 1/2 to the third power. I can rewrite this one as 180 times 1/2 to the second power. I could even write this one as 180 times 1/2 to the first power. So my explicit rule, to write this all out, I can say, I guess I could use A in this case since we're told this is population A. So I'll say A of n equals, now here the 180 isn't changing, and the 1/2 isn't changing either. That's always going to be the case when I'm writing my explicit rule if it's geometric. I'm going to have my starting term times my growth factor and then raised to a power. Now this time the power is the thing that's changing, so that's where my variable is going to show up. And on this problem, the exponent matches up with the term number that I'm on, in this case the time in hours that have passed. So this problem, or this formula, would just be 180 times 1/2 to the nth power. My domain then tells me where to start, what value to plug in first. It tells me that I'm starting with term 0. So, and again, we can double check that by actually plugging 0 into the formula that we just wrote and making sure that we get out 180, and we would if we plugged 0 in for n. All right. On number 11, this one, it might help if I list out my terms again. So term 1 is 20, term 2, 10, term 3, 5, and term 4, I don't know, it looks like maybe about 0.5. So, I mean, hopefully we can tell that this one is not arithmetic. I can tell that I'm not adding the same thing, right? To go from 20 to 10, I would be adding -10. To go from 10 to 5, I'd be adding -5. So hopefully we can quickly tell it's not arithmetic. Let's test to see if it's geometric then, right? So I want to take a term and divide by the previous term. So if I take 0.5 divided by 5, well, that's going to get me 0.1, right? So I'll say this one, I would have to multiply it by 0.1 to get from 5 to 0.5. And then if I take 5 divided by 10, well, that's 1/2. And 10 divided by 20 is also 1/2. So in this case, it appears that this sequence is geometric to start, right? I'm multiplying by 0.5 to go from 20 to 10, and then multiplying by 0.5 to go from 10 to 5. However, to go from term 3 to term 4, I am not multiplying by 0.5. That means that this sequence is neither arithmetic nor geometric. On number 12, we want to use the graph to write a possible equation for this polynomial. What we want to focus on are the x-intercepts. That's going to let me write a factored form of this polynomial. So if I have an x-intercept of -5, we have to think, well, what factor did that come from? When we're determining x-intercepts, we have to set our factors equal to 0 and solve. So an x-intercept of -5 would have come from a factor of x plus 5, okay? If I have an x-intercept of +1, that would have come from an x-intercept, or a factor of x minus 1. And if I have an x-intercept at +4, that would have come from an x-intercept, from a factor of x minus 4. So this would be my polynomial equation that matches up with this graph. On number 13, we're just going backwards from number 12. We are given the function, and we have to determine the x-intercepts. So what I'm doing is just setting each of those factors equal to 0 and solving. So for the first one, all I have to do is add the 7 over, and we get that one of my x-intercepts would be at 7. For the second factor, I'm going to have 2 steps. Start by subtracting the 5 over, and then dividing by 3 to get x by itself. So this factor would give me an x-intercept of -5/3. And my second one, subtract the 9 over, and we get -9. So 3 x-intercepts of 7, -5/3, and -9. On 14, find the zeros. That means x-intercepts. This is a quadratic, So our best strategy for finding the zeros of a quadratic is to x factor. Right? So in my x factor, up top is a times c. Now remember, the standard form of a quadratic is ax squared plus bx plus c. So a times c in this case would be 1. My a value would be 1 times negative 24. So I'm going to put negative 24 up here, and then my b value goes in the bottom, which is 2. So what I'm looking for are two numbers that multiply to negative 24 and add to positive 2. Now, we can use our calculator to help us with this. If we want to think about all the factors of 24, we talked about in y equals in the calculator, we could type in 24 divided by x, and then go to the table to get a list of the factors, right? But I mean, I'll just list out the factors here. 1 times 24, 2 times 12, 3 times 8, and 4 times 6, right? Those are all my factors of 24. Now, if I want my two values to multiply to a negative but add to a positive, I know one of them is going to have to be negative and the other one's going to have to be positive. So looking at my list here, I need to figure out which pair of factors, if I make one of them negative, will add to 2. Well, it's going to end up being the 4 and the 6. If I make the 4 negative and the 6 positive, then they will multiply to negative 24 and add to positive 2. Now, at this step, don't forget that we technically need to divide by my a value. In this case, however, my a value is just 1, so that's not going to change anything. I'm still just going to have negative 4 and 6 here, but don't forget that step. Right? If my a value is anything other than 1, that will change the rest of this problem. Now, that means that I can write this problem in factored form of x minus 4 and x plus 6. Now, to find the zeros, now that I have this in factored form, all I have to do is set each factor individually equal to 0. So for this one, I would just have to add the 4 over and get x equals 4. For this one, I would have to subtract the 6 over and get x equals negative 6. On number 15, this one we are just told that our function has an odd degree and a negative leading coefficient, and we wanted to sketch the general shape. So this question is getting at these end behaviors of polynomials that we spent a lot of time talking about. I would probably try to memorize these 4 scenarios. So if we had an odd degree and a positive leading coefficient, my graph had this general shape for my end behaviors. Odd degree and negative leading coefficient, which is this scenario. This number 15 is asking for this general shape here. But then if I had an even degree and a positive leading coefficient, both ends were going up. Even degree, negative leading coefficient, both ends are going down. Again, I would highly recommend memorizing these 4 scenarios. On number 16, what is the constant term of this polynomial? Now, when we worked with polynomials like this that had exponents on some of the factors, one thing that I recommended was just writing out every factor. So what I mean by that is if I have x plus 4 squared, I'm going to write it out as x plus 4 times x plus 4. And then if I have x minus 3 squared, I'm going to write this out as x minus 3 times x minus 3. And then just one x plus 8. So, to find the constant term, all I need to do is multiply any value that I have out in front, any coefficient, times all of my constants. So 1/2 times 4 times 4 times negative 3 times negative 3 times 8. And if we put that into the calculator, we should get 576. So 1/2 times 4 times 4 times negative 3 times negative 3 times 8 tells me the constant of this polynomial would be 576. Now, if we wanted to graph this, that would also tell me the y-intercept is positive 576. On number 17, the points of intersection between these graphs. Well, to find points of intersection by hand, I need to set these two functions equal to each other, right? So I'm setting f of x equal to g of x. So x minus 5 times x plus 3 equals x plus 3. Now, we said we want to get everything on one side equal to 0. So what I'm going to do is subtract this x plus 3 over to the other side. On the right side, these will cancel out. When I'm subtracting something from itself, that cancels out and just equals 0. On the left side, though, these x plus 3's do not cancel out because this first one is being multiplied by something else, by x minus 5. So I'm just going to write this whole left side as x minus 5 times x plus 3 minus x plus 3. Now, at this step, I want to look for a GCF. Both of these terms do have an x plus 3 in them. So I'm going to factor out an x plus 3. And everything that's left over is going to go in my second set of parentheses. Now, what I'm actually doing when I'm factoring something out, I'm dividing each term by that thing that I'm factoring out, in this case, x plus 3. So in this first term, when these x plus 3's cancel, right, when something cancels out between the numerator and denominator, that equals 1. Anything divided by itself is equal to 1. So this term just becomes x minus 5 times 1. Well, x minus 5 times 1 is just x minus 5. Same thing over here. When these cancel out, they equal 1. There's nothing to multiply that by here, so this just becomes minus 1. So I've got another minus 1 here. So I can simplify what I have in my parentheses there. X minus 5 minus 1 would just be x minus 6. So now I can set each of these factors equal to 0 to get the x coordinates of my points. When I set x plus 3 equal to 0, I'm going to get x equals negative 3, and when I set x minus 6 equal to 0, I'm going to get x equals positive 6. So far, what we've determined is we have 2 points of intersection. One of them has an x coordinate of negative 3, and the other one has an x coordinate of 6. I still need to get my y coordinates. To do that, I'm going to plug each of these values back into one of my original equations. It does not matter which one. It looks like g of x would be easier to plug things into. So let's start by plugging negative 3 into g. So g of negative 3 is just going to be negative 3 plus 3. I'm just replacing x with negative 3. Negative 3 plus 3 is 0. So that tells me the y coordinate of this point is 0. If I plug in negative 3, I get 0. Well, let's do the same thing for 6. If I plug 6 into my function, well, that just becomes 6 plus 3. 6 plus 3 is 9, so that tells me the y coordinate of this second point of intersection is 9. On number 18, to determine if something is a factor, we want to divide. Synthetic division is probably the easiest way to do that. So if I set up synthetic division up here in my box, I need to figure out what value is going to make this divisor equal to 0. So negative 2 is what would make this equal to 0. We could write that out and say x plus 2 equals 0 and solve that little equation to get negative 2. Then I want to list out my coefficients, 3, 5, negative 2. And to go through my synthetic division process, bring that first value straight down, multiply by what's up in my box, add straight down, multiply, and add straight down. The remainder is the key to determining if something is a factor. If we get a remainder of 0, that means yes, this is a factor. If we would get any remainder other than 0, that means that x plus 2 would not have been a factor. On number 19, to find the vertical asymptote, we are just looking to see what value of x makes the denominator equal to 0. Well, we can write it out and say x minus 3 equals 0, solve for x, so add the 3 over, and we get that the vertical asymptote is just the line x equals 3. On number 20, to determine the end behavior, we need to divide. Right? So I need to set up a synthetic division problem. Up here in my box, I need to put the value that's going to make the denominator equal to 0. That would be -4, and then I need to list out my coefficients of the numerator. So that would be 1, 7, -1, and 5. So if I go through my synthetic division process, bring this first value straight down, multiply by what's up here in my box, add straight down, multiply, add, multiply, what is that, 52, and add. So this tells me, since I started with a third degree equation, my result then is a second degree equation. These would be the coefficients on 1x squared plus 3x minus 13, and then the way that I would write my remainder would be plus 57 over whatever I was dividing by, over x plus 4. Now, the end behavior comes from my result here ignoring the remainder. So what I can say here is as x approaches both positive and negative infinity, f of x approaches the function y equals x squared plus 3x minus 13.